All right. So the next step is we are going to now develop the idea of potential energy, energy that can be associated with a particular force, and these forces are going to be what are known as conservative forces. So thinking back from introphysics, mgh, 1/2 kx squared for a spring, negative g mm over r for Newton's universal law of gravity. Those are going to be the common ones we will be thinking about in this class. Let's do a quick reminder of where we were last time. We defined work, we defined work to be the integral of the force over a distance. What is the force dotted with the distance vector, as you kind of trudge along? What amount of work is done by the object, and then we show that that is equal to the change in kinetic energy of the object. 1/2 m v final squared minus v initial squared. How does kinetic energy change when forces do work on an object? And we had a couple examples before where we started at, I believe we started at the origin and ended up at 1, 1 through a variety of paths. In one of those paths, we took a straight line that just went diagonally up at a 45-degree angle. And I believe we found the work there that was done was 0. So there would be no change in kinetic energy if that was your path. There was a parabolic path that we took. We found the work there was a third, I believe, a positive a third. So there would be an increase in kinetic energy from that path. Then we did another path that did it piecewise, first purely horizontal, then purely vertical. We found that that gave a total work of 1 unit. In this case, there would be an increase in kinetic energy. And by the way, what are the units here? Well, the units of work, or the units are obviously going to be the same as the units of kinetic energy. So it looks like it's kilograms meters squared per second squared, which we define to be the joule as the unit of energy. Now let's think about, again, geometrically, why the blue and the red curve result in speeding up while the black curve resulted in no change in your motion. You did not speed up or slow down. Remember we said that work being positive meant speeding up. If we go back to the work energy theorem, then if we're speeding up, that means that this right-hand side is positive, which again means that you have to do positive work. Which means this integral, which is you're counting all the little pieces of f dotted dr as you trudge along your path, that there's more positive ones of these than there are negative ones of these, of all those little calculus bits. So in the case where you're speeding up, that means these are more positive than negative. Well, we can think, when was the dot product positive again? Well, the dot product is the product of magnitudes times the cosine of the angle, where cosine is 1 when they're parallel, 0 when they're perpendicular, and then negative when it's more than 90 degrees. So geometrically, if we're thinking about this, when we're speeding up, that is when f dot dr is on average always greater than 0. And that occurs when the two vectors are closer to being parallel to one another. Or might be exactly parallel to one another. In that case, the dot product is positive, and that contributes positively to the amount of work you're doing. Similarly, work being negative, we said was slowing down, which by the same sort of reasoning, that means f dot dr on average is less than 0. Again, when was the vector dot product negative? That's when the angle between the two was greater than 90 degrees, so they are closer to being anti-parallel than they are to being parallel. So this would be closer to anti-parallel. And then when was the work equal to 0? So no speed change. Again, as a reminder, your direction might be changing. For example, think uniform circular motion. Your direction is constantly changing, but you're not speeding up or slowing down. There's no work being done, in that case, by the force that is causing you to move in a circle. And if you think of what was the geometry in that case, well, in this case, that's when f dot dr must be equal to 0, which is the case when they're perpendicular to each other. So if we look at the black curve, for example, that was the one where we talked about how all these force vectors are at a 90-degree angle to the path you're taking. So again, as you walk along that diagonal path, the force that you're feeling as you walk along that path is neither at your back or in your face. So it's not speeding you up or slowing you down. And so there's no change in your kinetic energy. Where if you look at for the blue and for the red, then in those cases, the arrows are closer to being parallel than they are not. Take this case, right? The arrow is kind of pointing in that direction while your path is going vertically upward. Those two vectors are closer to being parallel than anti-parallel. In the case of the blue, in this case, kind of the vector here is pointing that way, which might be closer to being perpendicular. But let's see, here, right here, I guess your arrow is kind of pointing right like this, while your path is kind of pointing like this. Those two vectors are closer to being parallel than anti-parallel. So in that case, you will then, as a result, be speeding up. So these are kind of geometric examples of what's going on with work. And again, it's kind of the same thing we've talked about before. The parallel component speeds you up and slows you down. The perpendicular component changes your direction. Energy, in a sense, is kind of honing it or zooming in on what's going on with those parallel components, since that will change speeds as a result. What are some other results we also laid down? For position-dependent forces, when you go from A to B, that is going to be the negative of the integral you get when you go from B to A, which might seem familiar from regular integrals. That also holds for line integrals, for these position-dependent integrals. If it depended on velocity or time, that might not necessarily be the case, but when it's position only, then this holds. So notice in this case, there are possible paths. Let's see, let's simplify this a little bit. Let's take just the red and the black curves that I had, and let me redraw it. So starting at 0, 0, going out to 1, 1. You had the black path, which was just a pure diagonal. Then you had the red path, which was that right there. And when you did the red in kind of the counterclockwise direction, that was +1. And then when you did the black, you got 0. So then, similarly, if I did the path for the black curve in the opposite direction, going from B to A, I would also expect my work to be 0, -0, I guess. Because even if you're going in the opposite direction, your path is still always perpendicular to the direction the force is pointing. Where if I took the path in reverse from B to A along the red curve, I would get -1 joule, say, of work that's being done as you went along that path. So you can say things like, if you wanted to do a closed loop of the force, which I'll specify with a little circle, some path that starts back where it started. Now, this were a regular integral, we'd immediately say it's 0, or the integral of a function from x equals 0 to x equals 0, right? You just write down integral 0, the area under the curve is 0. But for a line integral, that need not be the case. In this case, you could say you could take the red path of f dot dr, and then take the black path in reverse, in which case you would expect to get +1 by taking the red path, +0 when you took the black path in reverse. You complete a full loop and you would have a change in there would be a net amount of work being done by doing a loop. So you would end up back where you started with more energy than you started with. So you could keep doing this loop and you would speed up and speed up and speed up every time you repeated this loop. Or if you did it in reverse, right, I could say that's different than if I go f.dr in a loop, where instead I go first the black path from A to B, and then I do the red path in reverse from B to A. I would then get something like I get no work from the black path, and then I would get -1 joules by doing the red path in reverse. And so by doing black and then backwards on red, I would lose energy every time I looped around. So if I did that loop over and over and over again, I would constantly be slowing down as a result. So in that case, you can end back up where you started, but not necessarily have, come back to the spot with the exact same conditions you had when you started with. Your kinetic energy could be different in those cases. That seemed to not be the case with gravity, or at least for the examples we looked at last time. We looked at the example of kind of a ball falling, and there was some amount of work that was done. And then we did the other example where the ball moved down a ramp of arbitrary angle theta. So in a way, we kind of considered an infinite number of different paths, or you can consider every possible angle between 0 and 90 degrees. And all of them resulted in the same amount of work being done as the apple went from the top and then ended up on the bottom. We could do that in reverse and consider what if you then had some amount of energy at the bottom of the ramp and I just threw the ball up. Or if I just throw the ball up vertically, it's pretty easy to figure out how high it's going to get for a given initial velocity. You can then calculate the amount of work that's being done. You could then throw the ball up a ramp of arbitrary angle and calculate how far does it go before it stops, and how much work is being done, and you would yet again get the exact same answer as both what you would have when there is no ramp, and it would be the exact same amount but negative as what we computed in the last module when we were letting the ball fall or roll down the ramp as a result. So in that case, you could imagine that the ball could, say, fall down, go through some circular track that would change its direction but not its overall velocity, and then essentially launch itself back up an arbitrary ramp, and it would end up back exactly where it started with the exact same energy that it had when it started. If it was released from rest, it could fall, do some sort of loop that then moves it back to the ramp, then it could move back up and would return back to where it started with 0 kinetic energy. Right, I could imagine you could do like circular motion or something like that to do this, right? You could have some sort of ramp that if the ball rolls down, then it goes through some sort of track that's frictionless and goes through, say, 2 3/4 of a circle. Then it could end up, say, back at the base of the ramp, and its energy would not have changed at the bottom of the ramp. It's kind of weird perspective here. It's kind of, here, maybe I'll do it 3D, or try to do it 3D. Where it goes down the ramp and then kind of goes into the page and kind of out of the page and then kind of comes back here. And if all that was horizontal and frictionless, the ball's kinetic energy would not change at any point along this trajectory, because it would either be moving in a straight line and be frictionless, so gravity wouldn't be doing anything, or when it's going along in a circle, the force that is being done by the ramp as the ramp changes its direction would always be perpendicular to the direction the object's moving. So that circular part of the loops would not be doing any work either. It would not be speeding up or slowing things down, kind of like uniform circular motion. Then it could get back to the ramp, and it would make it exactly back to where it started, and it would get to the top of the ramp, not with more energy, not with less energy, but with it would be exactly the same as what it started with. And while that's an infinite number of possibilities, there are other possibilities you can try too, right? You could have a ramp, but you could initially throw the ball up a ramp and then it would stop and then fall back down. And then you could calculate how fast it's going when it gets to the bottom of the ramp. That would end up being the same amount of work as if you released it from rest at the top of the ramp and it rolled down, for example. Or at least gravity would have done the same amount of work. The kinetic energy would have changed by the same amount in those cases. And you can imagine there's all sorts of other paths you could try of how it can start at the top and end at the bottom. And in all of the cases with gravity, the gravity would always be doing the same amount of work. It would start at the top and end at the bottom. No matter how it got from top to bottom, gravity would do the same amount of work overall. And similarly, if you then went in reverse through the ball back up towards the top, you would find that gravity would do the same amount of work getting from the bottom back to the top, but with a negative sign. So in that case, this is motivating that there are some particular forces that we are going to be particularly interested in. Particularly interested in. Forces where I can say something about, if I evaluate the work that force does over some sort of closed path. There are cases like what we saw with gravity where that closed path is equal to 0. We haven't really proven this yet, but for any closed path. Again, if it starts up here and ends down here, no matter how it gets from here to here, straight line, zigzag, ups, and then comes back down, gravity ends up doing the same amount of work and then ends up, reversing itself to go back. This integral would hold for no matter what path of the infinite possibilities you could dream up would occur. These particular forces where this is true are called conservative forces. These forces where this kind of closed loop integral is 0 are what we call conservative forces. Because if this condition is true, a variety of interesting mathematical properties emerge. One that ends up being what we ultimately call the conservation of energy. And just to motivate this a little bit more, maybe let me put 2 other vector fields down and we can talk about them a little bit. So here's one where it'd just be kind of uniform gravity. And then this one, which is kind of an attractive force, that's kind of a central force. So this might be something like Newton's law of universal gravitation. So this one might be kind of F equals in 2D 0 dot negative mg. And this might be something like F is gmm over r squared or negative that, all in the radial direction, using polar coordinates. These end up also being 2 examples of conservative forces. And you can imagine some examples, like I can imagine in the case of uniform gravity, if I were to do a path that, say, just kind of drew out a box. If this is x and y, for the axes, where I move horizontally, I start here, I move horizontally right, then I move vertically up, then I move horizontally left, then I move vertically down. By the symmetry of the situation, you might be able to convince yourself that there's going to be no net work done. In the cases where it's horizontal, we expect there to be 0 work being done, because again, the force vector and your path are perpendicular. When you're going up, you're anti-parallel to the force, so I expect there to be negative work being done there, some sort of negative W. But then by symmetry, I expect that this was then going to give me positive W, and it's going to be the same W on the left-hand side. And if you add up 0 minus W plus 0 plus W, that all adds up to 0. Right, or you can imagine a path where maybe I start here and I do some sort of diagonal. Well, again, by symmetry, it seems like this is going to have some sort of negative W work if I'm going counterclockwise. Similarly, this is probably going to be negative W work, again, by the symmetry of the situation. It's the same length of path, and you're at the same angle relative to the force vector. And then these are going to give you positive W on each side. And they're going to all add up to 0. Or in the case of, say, a ramp, you start here, you go straight down, you move horizontally over, and then you shoot straight back up. And you get some sort of positive work here, 0 work here. And then we worked out the examples last time where this ended up, or I guess you could work out the example of going back up. You would again get kind of negative, the same amount of work, but negative as you went back up. Longer path, and now you're at an angle with the force, but those kind of work together to everything balances out. And similarly for Newton's law of universal gravitation, right, you could imagine starting here and doing something like this. Again. And here it's a little harder to immediately kind of imagine that this is all going to add up to 0, but you can see at least on the left you expect the work to be negative because you're more anti-parallel. Here you're more parallel. Here you're more parallel. Here you're more anti-parallel. And so it is at least conceivable that those all could possibly add up to 0. And here while all the arrows are the same length, the color is corresponding to magnitude as you go farther out. But again, these are just kind of specific examples where the work adds up to 0. That does not prove that this is true for any arbitrary path I could draw, right, which could have as many kind of complex zigzags as possible. What's the guarantee of that zigzag path, or if I draw it over here, that this zigzag path, if you took that as your trajectory, that the work is going to add up to 0 in that case? You can at least imagine that it's conceivable, because there are times along the path where the work is going to be positive, times along where it's going to be negative. So it's conceivable that you could have that add up to 0 in some way. But again, how do we prove this? And so let me just sketch out the proof. I'm not going to prove it rigorously. I don't know if you would do this in Calc 3. I definitely did this in upper level real analysis, but let me just sketch the proof, and you can look at a mathematical methods book for the full proof. So let's simplify our lives and imagine that there's only one force acting on the object. If we can do it for one force, then it's just kind of a superposition of you add all the forces together for multiple forces. So this force, if I want it to be as general as possible, could then be a function of position, could be a function of velocity, could be a function of just time itself. Right? A position-dependent force, or a constant force, or like a friction or air resistance, which might include velocity, or it might be some sort of time-varying force, right? It's a fan that's hooked up to a motor that you turn on and off at regular intervals, right? The amount of air resistance, say, or wind that's pushing against you will change depending on whether it's on or off. So starting super generally, a conservative force we're going to say is one where F dot dr, the work done as you go from point A to point B, is the same for any path. Between A and B. A is here, B is here. One path could be straight over versus arc versus some squiggly line that gets over. No matter what path I draw, how you start, as long as you start at A and starting at B, we're going to say a conservative force has this integral has the same value for any path between A and B. And we're going to improve that and say in space and time and for any initial condition. So all that matters is that you start at A, you end up at B. It doesn't matter if you were initially moving super fast or super slow, or if you do it today or 10 years from now, that this is the same. The amount of work being done, if we want to think physics, the amount of work being done is the same for any path you could draw. This is a statement of path independence. There are implications right away by just this statement alone. One of them is that this restricts us that these forces that are conservative can only be forces of position only. You can't have it depend on velocity. Imagine air resistance. Because that means the amount of work that would happen, or if you have air resistance, which depends on velocity, how fast you're moving through the air, that means you will have a different speed. You know, if you go from A to B and you start moving really fast, you're going to feel more air resistance. Or if you start moving really slow, you're going to feel less air resistance. How much work gets done, which then tells you how much your kinetic energy has changed, will depend on kind of your initial conditions. So that requirement kind of rules out any dependence on velocity. This also then has to rule out any dependence on time, because again, if it's the same for any path between A and B, and this is any path in space and time, it can't be the case that I go from A to B in a straight line today and get one value, and then I go from A to B tomorrow and get a different value. Then it would not be path independent, because those paths, while the same in space but different in time, are giving you different amounts of work. So if we're going to be truly path independent, then there can't be any it can only be a function of position at most. Constant forces are, of course, also possible. Pulling from last time, if it's a function only of position, then we saw that if you go from A to B, that's some amount of work. That's going to be negative the amount of work that you get from going from B to A. So if you go in the path in the opposite direction, same amount of work, but different sign. And then these together then imply, kind of what I had written down before, that for any closed loop, it must be 0. For any loop that starts at A and ends at A. And that's not too bad. That's not too hard to prove. If I have, here's A and here's B, how can I prove that the work done by doing a loop is 0? Well, let's imagine I go from A to B, and that amount of work is W. But then I also go from A to B to this other path, and that amount of work is there's some other amount of work that's done, W prime. Well, by the assumption of statement 1, this also better equal W, right? If it doesn't matter which path you take, then the same amount of work it's done, that also is W. Furthermore, if I go from B back to A, that then better be negative W, because it's just negative the amount of work. Going from A to B was W in red, negative is then negative W in blue. And so in the case of a loop, I could do this and then do this. So I start and end at the same spot. That's one example of a loop where the total amount of work is 0. And since I never really made any assumptions about what these paths look like, I drew one straight and one curved, but that was just for the sake of the drawing. Since I had made 0 assumptions about what those paths actually looked like, this actually proves it for any possible path you can imagine. It's kind of a mathematical proof via abstraction, right? By making no kind of statements on the exactness of these paths, we have in essence proven it for every possible path that you can dream up. So, kind of big first takeaway, the loop rule, in that this is 0. There's no net work done if you end up back where you started for conservative forces, which we are kind of defining in this case. Kind of defining a conservative force is where that's the same for any path. But then we've showed that is the same thing as saying a conservative force is one where if you do a loop, there's no net work being done. So since this is arbitrary in terms of the path we take, I could also imagine a path that starts at A and does this, and that's some other path that takes you from A to B. But then that also better then require the same amount of work to be done. So if I had, say, some path C, or some endpoint C, and then took some path from A to C, I would not necessarily expect that the work being done here is the same as W. This might be W double prime or something like that, which does not necessarily need to be equal to W. Could be, but there's no reason why it should be. So it seems that the only thing that is determining the total amount of work that's being done is the endpoints. Tell me what's going on at the end, tell me what the endpoints are, and that will tell me how much work is being done. This again sounds like something from Calc 1, particularly the fundamental theorem of calculus, where you're doing an integral of a function, and really all that matters is you compute this thing called an antiderivative and evaluate it at the top endpoint, and then subtract from that the antiderivative at the bottom endpoint. Anything that kind of happens in between really is not, or it's in essence captured by the antiderivative, but in terms of just a pure mathematical function, really it's only, you need to know the value of the antiderivative at those two endpoints, and that's it. If you change the endpoints, the overall integral changes. There is a vector version of this, what is in essence the fundamental theorem of calculus, but for vectors, which is called the fundamental theorem of line integrals. So, since only the endpoints matter, when you're evaluating the work integral of f dot dr. Right, it only really matters kind of what a and b are. Or rather, if you know what a and b are for that particular force, it seems like there's something you can do involving that force that you can then plug in stuff about b and subtract from it something about a. So for the fundamental theorem of line integrals, where for regular integrals we said, there's this thing called the antiderivative, and then we plug in the value of, say, x at b, and the value of x and subtract from it the antiderivative of the value, of the antiderivative when you plug in the value of x at a. For line integrals, this says that there exists a scalar function, which I'm going to use u for physics reasons, such that what? And again, let's think of this in terms of Calc 1. Calc 1 is there's this antiderivative thing that, essentially it was the antiderivative of the integrand, where if I took the antiderivative and then took the derivative of it, I got back what was inside the integral. The integral of x is x squared over 2. X squared over 2 is the antiderivative. If I took the derivative of x squared over 2, I get back x, which was the thing in the antiderivative. So I should be able to take some sort of derivative of u and get back the force vector F. But I claim that u is a scalar function. So we have to think back, what can I do to a scalar function such that I get such that I get a vector back at the end of the day? Well, that's the gradient, such that negative the gradient of this function u equals the force vector. I take a scalar, I take the gradient, and the minus sign actually is a physics convention. If you look at this in a math textbook, there usually isn't a minus sign here. We're throwing in a minus sign just as a convention. That's fine. Such that if I take the gradient of this function, throw in a minus sign, I will get back the force vector. So that then, let me skip down here, the integral of f dot dr is then the same thing from a to b, is then the same thing as the negative, the gradient of u dot dr, which again, the gradient is a vector, so taking a dot product still is fine. But then again, think back to Calc 1, the integral of a derivative cancels each other out. So similarly, for a line integral of a gradient cancels it out. But then I have this minus sign thrown in as well. So then I have u at b minus u of a. And then there's an overall minus sign out front, which again is a physics convention. So again, it looks exactly like the fundamental theorem of calculus, but this is for line integrals instead. So what this says is we've motivated that for a given conservative force, there exists this scalar function, which I'm going to call the potential energy, such that if I take the gradient of that function and then throw in a minus sign, I will get back the force vector. It will have units of energy, and I can then work out, and it somehow must then relate to the work that that force is having done. Or we can just think again that if f dot dr is the work going from A to B, and we can represent this force as some sort of potential function, we can further define a change in the potential energy delta U, not gradient of U, but delta U, for some function U, which is a function of position. It's not a vector, but you might need knowledge of your position in order to evaluate it. such that what? Such that the change in potential energy is going to be negative this integral, this work integral, which again is just, then it looks like it's negative the work. You're going from A to B. And again, that negative is the same negative from before that's being thrown in for physics reasons, which we're going to see in why in a second. And then what is this U? The U is such that the force vector is retrieved by taking the gradient of U with a negative sign. So this motivates that there is a function that exists that can do this. The path independence motivates that it only depends on the endpoints, and so that this function probably exists by the fundamental theorem of line integrals. Well, probably exists, it does exist. And then we can define it such that it is saying something about that the work, we're going to relate work to potential energy by saying that the change in potential energy, the change in this function, U final minus U initial, is negative the work that's done from going from A to B. And so the way you can then mathematically define U sub r. How can we mathematically define U sub r? Well, we can motivate it by this idea here. The change in potential energy is negative this integral and going from A to B. Right, so you could think of this left-hand side as U evaluated at B minus U evaluated at A. Let me make a point that is important. Actually, so important, I'm going to move this down and come back to it in a second. This is saying that changes in U, right, the delta U, relate to work. If you want to talk about how much work a force has done, or similarly how much a potential energy has changed, right, it's the change in potential energy that relates to work. It's not the exact value of the potential energy, but only the amount that the potential energy has changed. So changes in potential energy relate to work. Only delta U has any physical meaning. It means nothing if you tell me the potential energy of this ball is 5 joules. That means nothing to me unless you give me some more information. It has some meaning if you tell me that it has 0 joules of potential energy when it's at the floor, because that is telling me in going from the floor up to this point, there's a change in potential energy of 5 joules, which means the amount of work it can do in going from my hand to the floor is 5 joules of work on an object. Just saying that it has 5 joules right here doesn't mean anything unless you give me some context of what it means to have 0 joules of energy. Similarly, I could say this is the location where the object has 0 joules of energy. And then if I said if it went down to the floor, I would then expect that it would have then, say, negative 5 joules of potential energy at the bottom. And again, it's the change in potential energy that tells me how much work is being done by gravity as the object falls. So only changes in potential energy have any physical meaning. And again, we can see that here, because it's saying that changes in the potential energy relate to work. That means there is some freedom in terms of the values we can give to potential energy. Since only changes matter, I can, for example, define this location as having 0 joules of potential energy, or maybe this location has 0 joules, or maybe this location has 0 joules. It doesn't matter as long as I state kind of a reference location, because again, it's only how the potential energy changes in going from from one point to the next that matters. So you can mathematically define U sub r by using a reference point. R sub naught. And that R sub naught is where we're going to decide that U at R sub naught is equal to 0, which you are free to choose most of the time, as long as you don't end up dividing by 0 or something like that. So essentially, you're just marking where you're calling the potential energy 0, which can be different for everyone, because again, only changes in potential energy matter, and ultimately this has the flavor of just an arbitrary constant that is added on. So then you can define U at R as being negative the integral from the reference point to your location f dot dr. That is the formal mathematical way of defining the potential energy function. Starting from some reference point, do the line integral out to some arbitrary location, and that tells you the value of the potential energy function at that location, at that arbitrary location, with the information baked in that you're making the assumption that the potential energy is 0 at a particular reference point. So thinking back to just constant gravitational force, right? You might remember that the potential energy function was just mgh or mgy. Well, that was making an assumption that at y equals 0, that's where the potential energy is 0. I could equally have said the potential energy function is mgy plus 3. That would have been an equally valid potential energy function, or mgy minus 10 divided by pi. That would be an equally valid potential energy function, because when I look at changes in the potential energy, well, that constant is going to get subtracted away. It's going to be mgy plus 3, and then subtract, say, mg, a different y, plus 3. And the 3's go away, so who cares? Because again, it's only changes that matter. All right, I think I've beaten that idea to death. An implication of this, the big result, perhaps. If only conservative forces do work on the object, then I can say that the change in kinetic energy for that object, which is equal, of course, to the work that is being done on the object, it's the work energy theorem. But if this is work by a conservative force, then there is a potential energy function U such that, it's off the screen at this point, such that I can say the work being done by that conservative force is going to be negative the change in potential energy for that particular force. So I can then say that that work being done was actually negative the change in potential energy being done by that conservative force. So in this case, it looks like delta T equals negative delta U. And here's where that minus sign convention becomes more obvious. Let me move delta U to the other side. Then it looks like it's delta T plus delta U equals 0, or that's saying that delta T plus U equals 0 in this case, which is, of course, conservation of energy. So that negative convention allows us to then be able to say something that, T plus U has no change. If we didn't throw that minus sign in, it would be saying that T minus U has no change. And again, since it's a mathematical function, we can define it how we want. So this is technically conservation of mechanical energy, I think is how it's typically framed. Of when you only have conservative forces doing work, energy is conserved. This energy is conserved, kinetic plus the potentials. It only matters about the endpoints. Does not matter how you got there. I can say the same thing about this ball that starts here and ends here. That's the same sort of argument as a ball on a string that starts at the same spot and ends at the same spot, though it takes a different path by kind of swinging down. Because again, while there's a force from the string, if it's sweeping in an arc, you can convince yourself that the string is not doing any work on this object because it's always perpendicular to its motion. So gravity in both of those cases are the only conservative force doing work. And if they're only conservative forces doing work, then the conservation of mechanical energy applies. All right, only 50 minutes. Not as bad as I thought. There's actually one more result from this. So we've started from this idea of defining a conservative force as being path independent. That means it's zero for loops. That means there's a potential energy function we can define. And that means if there's only conservative forces acting in the object, you have this statement of conservation of energy. The last thing is, how do I know if a particular force is a conservative force? Because again, I'm not going to take the time to evaluate F dot dr for every possible path between A and B to assure myself that it's a conservative force. Is there a test I can write down that would immediately allow me to say that no matter what path I take, it's going to be independent in terms of evaluating the work? Spoilers, yes, there is. So kind of the last statement of all of this, right, which I call the test of how you can determine whether or not your force is a conservative force. And this makes use of the vector identity. That the curl of a gradient function is equal to 0. Remember, the curl is a vector function that I guess I never technically before wrote down the gradient, but presumably you remember. For Cartesian coordinates, it's partial u dx, comma, partial u dy, comma, partial u dz, etc. If you're in polar coordinates or cylindrical coordinates or spherical coordinates, you have to be a little bit more careful because it's not just du dr, du d theta, du d phi, or du dz. You can look at the cover of your book, and we'll talk a little bit about that in an upcoming module about other coordinate systems. And again, that's because remembering that the unit vectors change when you take derivatives, unlike Cartesian. Okay, that was an aside. So this vector identity is that the curl of any gradient is 0. That's not too hard to prove, actually. So if we given what I just wrote in Cartesian coordinates, remember that the curl is, again, it's like a cross product where I have I have j, I have k. Then the top row is the partial derivatives, d by dx, d by dy, d by dz. Then the bottom row is the components of the function on the right, which the x component of the gradient of u is du dx. The y component is du dy. The z component is du dz. Then I take the determinant of that. That gives me an answer. Let me just do it for the x component, and you'll see how this applies. So again, I do this subtracted from this. So it looks like in the x direction, I have the partial of dy applied to du dz. And then I subtract from that the partial with respect to z applied to du dy. That's in the x direction. Or I guess I used ijk above, so I stick with that notation, right? The x direction, or using the I hat component. But then, remembering our what we know of partial derivatives, this looks like it's the second derivative with respect to u, and it's a mixed partial. Sorry, dy dz, not dx dy, dy dz, and this also is du second derivative dy dz. Since you might recall that the order of the partials does not matter. So indeed, this ends up going to 0. And you can do it for the y component, you can do it for the z component, it all becomes 0. So the curl of a gradient is 0. So if this is true, but then remember the gradient of the potential function is related to the force. Particularly it's negative the force. So this says that the curl of negative the force vector is then equal to 0. We get rid of the negative sign. I can multiply both sides by a -1. This then says that the curl of the force is 0. That is the test. If the curl of a force vector is 0, then f is conservative. Essentially then, everything else applies. For example, a kind of trivial example, if the force is negative mg, which is a constant, in the y direction, say, well then clearly this is going to be true because the curl is going to always be involving some sort of partial derivative, but since this is a constant, whatever partial is going to turn everything into a 0 if it's not already. So in that case, that is a conservative force. You could go back up to our function above, where I had negative y comma x comma 0. You would find that the curl in this case is not equal to 0. So in that case, that function is not conservative. And not surprising, because we saw examples where you could take a closed loop path and you did not get that the closed loop work was 0. You can have net work being done when you end up back where you started. So there would be no potential energy function I can write down for this particular function. There is one I can write down for that, right? mgy, we'll derive it next time. There is one for Newton's law of universal gravitation, ends up being negative gmm over r, and that's the potential energy. Similarly for springs, the 1/2 k x squared, you might recall. Now I kind of proved all of this. Here, I want them all to be on the same screen. Let's cram this into the bottom. I proved all of these in a way going from top to bottom. It's actually a nice mathematical result that actually turns out all of these statements are equivalent. And that I kind of assumed the one I highlighted at the top, and from that kind of motivated the proof of everything that followed. Turns out there's actually an equivalence relationship where you can actually prove if you take any of these as an assumption, they imply the rest. So this is a tautology, or there's an equivalence relationship between all these statements that I've highlighted. If you assume one, they all follow as a result. These are all equivalent statements mathematically, which is a kind of nice result. But this gives evidence that there is this thing called potential energy that has all these beautiful properties when you can deal with potential energies compared to just arbitrary forces. So we'll derive a couple and do a problem or two in the next module.